the cosine. So whatever initial condition I have, plus the integral of cosine, which is sine, right? So 1 over epsilon, omega naught squared over delta squared, and here is the point, is that when you integrate, you get sine, and you get 1 over omega. And what is your omega? My omega was something like omega naught divided by delta epsilon. So it's always omega goes by 1 over epsilon. Okay? So this is with this guy, this is with that guy. So we have here x1, x2 plus omega naught over delta sine omega t sine theta, sine x1. Yeah, sine x1. And just, I will just, I will linearize for the sake of, you can continue entirely non-linear, but I'll just linearize because we don't have time. So this is x1, okay? So I got the flow, this is the flow of G, and if you like, you can write it linearly because I linearized. So this is like 1, 0, and omega naught over delta sine omega t and 1. x1, x2, okay. This is fine. And then we compose F with this guy. So what is F? Let's go and see F. So F takes x1, x2 and gives you what? The first element is x2, right? Remember, theta is x1, theta is x2. So F of any point is x2 at the beginning and omega naught squared x1. So F when taking a point, so give you the x2 of that point, so the second thing of that point, which is omega naught over delta sine omega t x1 plus x2, this is it. Okay? And then the second entry is omega naught squared times x1, omega naught squared times the first entry. So omega naught squared, the first entity is also x1. And you can also write it in this form, linear. 1 omega naught squared 0. The last thing is what? You multiply it with the Jacobian, right? The Jacobian of negative g, by the way. So from this we can get phi t negative g. Well, it's the same, just invert your matrix because it's linear. When I invert the matrix, I get, this is super easy, just change the sign here. So now my F, which is this thing with the Jacobian, I will just multiply the Jacobian here, which is this matrix, 1, 0, negative omega naught, whatever, 1 times whatever coming from here. Okay, anyway, whatever coming from here. So this is, let's do it together. So we have omega naught over delta sine omega t and negative omega naught squared over delta squared sine squared omega t, right, plus omega naught squared, and here is 1 and here is what? Negative omega naught over delta sine omega. Do it on your pace, that's fine. This is your F of t and x. Okay? And we have the g, but the g is just the cosine omega t kind of thing. So when we average, the g vanishes, and this is what will give us the mean. So let's average this guy. F bar, just average over time. Again, so this is 0 because it's sine. Here is sine squared, so we have half plus omega naught squared. Here it's 0, 1. And again, if we have damping, we could have added damping from the beginning. You will have it here, negative mu. So it gives us the same thing. If we now check that when this term is negative, if this is negative, if I want this to be negative for stabilization, so delta square needs to be less than half. Any questions so far? So this is the constructive technique. Apply the variation of constants formula before averaging. It's very rare that, so like I said, even the early pioneers like Lagrange and said they never applied averaging directly. They applied the variation of constants formula before averaging. The classical approach of averaging using perturbation techniques led by Naif and others, they never applied averaging directly. They have to apply the variation of constants formula. But they don't write it in that generic way. Using chronological calculus, we have now this tool that is useful, and in our language we can apply. Any questions so far? Any questions? So let's apply to mechanical systems in general and see what we get. And next time we'll talk about chronological calculus, and that's it. So application to mechanical system, or just mechanical systems. Any questions so far, please? Any question? So mechanical systems, they are systems written on this form, right? M of Q, S matrix, Q double dot plus Coriolis and centripetal forces equals, maybe you can add a potential, but it's just function of Q, plus we have our forcing term F of Q Uj, right? And when we invert, we get Q double dot plus M inverse C, this is Q and Q dot, equals M inverse is a function of Q and also the potential, so this is entirely function of Q, plus summation J 1 to M Yj of Q Uj, where Y is just M inverse F. Okay? And this is what we call what? This is what?
Geometric acceleration.
This is the geometric acceleration, right? Okay. And we do it in a first order, so d by dt is Q and Q dot is equal to, here is Q dot, and here is negative M inverse C. Again, it's Q and Q dot, and it's quadratic M velocity. It's anything in Q but quadratic M velocity. Here we have 0, negative M inverse angular V, it's function of Q only, plus summation 0 and Yj, again it's function of Q only, and Uj. Typically Uj is 1 over epsilon. So typically Uj is 1 over epsilon, high amplitude, high frequency, Vj, T over epsilon. So here we have, inside we have cosine omega t kind of thing, and outside we have 1 over epsilon for this is high amplitude, high frequency periodic force. So here we have Vg. The time part is here. And if you remember, this is what we called Yj lifted. And if you remember, what was that vector field? We just touched upon it, didn't dwell too much.
Something spray.
Yes, the geodesic spray. Well, you should remember the geodesic, but not the spray. The geodesic spray, S, it's the vector field whose integral curve, when you project it in the manifold, you get the geodesic, right? Because if anything else is 0 and you integrate this equation, you will get the geodesic. It's S, not delta. Okay, anyway, so now it's clear for us from the point of view of averaging that this is my vector field F and this is my vector field G, right? And I will go and apply the variation of constants formula and then average. And because G is 0 mean, V's are 0 mean, typically V's are 0 mean, so G is zero mean, so I don't need the second equation. I just need the pullback, large F, and average it out, okay? So, in order to get the pullback, we need to get the flow along G. I need to know what these guys look like, right? The flow along G and all of that. This is the strength of abstractness. So again, from chronological calculus, which we'll talk about next time, we can have a series solution or a series representation for F. It gives you F equals, actually if both F and G are time invariant, so by the way, note here, if F and G are time invariant, there is no time. Which we call what? By the way, we call autonomous, okay? I don't know if you heard this word before or not. Autonomous vector field is a time invariant vector field. So if F and G are time invariant, then this pullback, G star F, this can be, you can have a series solution for it from the Campbell-Baker-Hausdorff formula. Baker-Hausdorff formula. So this is not on a side. But my G is time varying. I will not be able to apply the Campbell-Baker-Hausdorff formula. So this is a generalization. But it's not for any F and G. F here is autonomous. G can be non-autonomous, that's fine. So for an autonomous F, time invariant, like typically the case